Hello and welcome to this seminar in intelligent robotics. Today I will be talking about UAV navigation in high dynamic environments using a deep reinforcement learning approach. So I'll start with the motivation, then the introduction, problem, approach, followed by the experiment, and then I'll talk about the results and discussions, and then the conclusion. Let's start by watching an introductory video. So as you can see, it was a nice demonstration of how UAV drone navigates by not hitting its obstacles. So it is one of the most commonly highly researched areas in UAV navigation nowadays. So UAV navigation deals with escorting an UAV from the source to the destination using a collision-free as well as using a short efficient path. Is it necessary? Yes. Is it absolutely necessary for the harsh environments where it is difficult for the humans to access, which can lead to life loss and also which can lead to the loss of precious time during search and rescue operations. So several deep reinforcement learning methods has been used for the navigation, but most of them has been tested in the static environments. One of the problem is that in highly dynamic environments we have the massive interactive data because large number of obstacles moving around. This causes the chaos of dimensions. Due to this, all the deep reinforcement methods, they face convergence issues. Hence, in this study we will be studying about a new improved deep reinforcement learning method, which is known as the layered RQN method. So as I spoke earlier, the UAV navigation is a complex multi-objective problem which is divided into hierarchies. So in our problem, we'll be also dividing the problem into several sub problems. First is to avoid the obstacles, which is done by the avoid network. Second is to have a separate network, which is to find the efficient way to the targets by calculating the maximum amount of rewards. And through this entire process, we have to determine the position and the speed of the different drifting obstacles. So this is a special temporal task. For that we are using LSTM, which is a special type of neural network. We'll talk about this later. Finally, we have a clip DRL loss function. It is part of a third part, which is known as the packed method. So here it chooses an action whether to avoid and acquire and then combines them in the loss function. So as we are using a deep reinforcement learning approach, let us look in some of the basic of reinforcement learning. So reinforcement learning is a learning by doing. It is unlike the supervised learning techniques. Here an agent takes an action based on a situation and it tries to find the reward, and it tries to finally reach the goal with the maximum number of rewards. A reinforcement learning scenario can be described as a Markov decision process, which contains a finite set of states, a set of all possible actions, a policy function which maps an action taken at a particular state at time t, and then doing the transition to state t plus 1. Then we have an instantaneous reward after an action is taken, and also a discount factor. Discount factor is determines the amount of the Q values which are taken from the next steps. We will talk about this much more bit later. So here we can see a pictorial representation of the Markov decision process. The agent is taking an action in an environment, and then it is getting the reward in the next step, and it also moving into the next time step, and then it continues again and again. We also have a value function. Value function measures how much valuable an action is in a particular state. Also, there is a policy function. The policy function chooses the best action, that is the action with the highest Q value. In our experiment, our scenario consists of several obstacles. The red ones are the highly dynamic ones, the orange are the medium dynamic obstacles, then the yellow ones, which are the least dynamic obstacles. And in our problem, our goal will be to navigate the UAV from the origin to the target by keeping the distance from the obstacles minimum and also reducing the path length. So for an UAV, it has several observation vectors. So these are all 16-dimensional vectors. These are given from the ultrasonic range finders, the LiDAR finders, which senses the environment and gives the UAV different information. So these are the distance in 16 dimensions of the UAV from each of these obstacles. Also, we have the absolute position. The absolute position measures the angle between the UAV's line of sight and the x-axis. Then the relative position, which is the angle between the UAV's line of sight and the target. So all these three vectors forms the state vectors in the state space. Also, we know that in a UAV there are 3 degrees of freedom in which it can move: the roll, the pitch, and the yaw. The yaw angles, they form the action vectors. So the action vectors are also 16 dimensions. So each of these vectors is calculated by the difference between the angle when the agent is taking the actions in a state t+1 and then in a state t. Furthermore, we can say that all these action vectors, the states as well as the rewards, they are grouped together to form an episode. And at the end of the episode, the agent performs a transition from a state t to t+1. Also, that the policy function that we were talking about in the previous slides, the policy function is learned using a Q-learning algorithm, which uses a greedy approach. As you can see, the next value of the Q value is updated by adding the previous Q value and then the sum of alpha. Alpha is the learning rate here, and the reward, followed by a gamma portion of the maximum amount of the Q value in the next time step. So the gamma determines how much amount of Q value we will consider while updating our current Q value. So it is the discount factor. So the layered RQN, it consists of the 3 parts as we spoke about earlier. The one is the avoid network to avoid the obstacle, the acquire network to acquire the target, and the pack network, which combines both of them and chooses an action. So each of these networks are further broken down. As we can see, they consist of several LSTM cells, and for each LSTM cells, it performs an operation and calculates the Q value. So the Q value for LSTM cell is given here in this equation, and the theta are the parameters of the LSTM. We also see that each LSTM is associated with certain history because it analyzes the temporal data with different time movements. But here in this method, we are not taking the history for all the states and actions in an entire episode. Instead, we will be calculating the history at each time step by adding up the history of the previous time step and combining it with the action and the state currently taken. This supervised data is then used to update the Q value of the target network. And in the target network, we will be having a cost function. The cost function, which is used to measure the loss. Here we measure the loss between the true value and the value from the Q value which is acquired by the network. Finally, we are using a stochastic gradient descent algorithm to update the parameters of the network. So we can see a highly complex navigation task is distributed into much simpler tasks layer by layer in this network. Hence, we gave it the name the layered recurrent queue network. The clip loss function that we have as the third layer, it is used to combine the two the results of the two networks, the avoid network and the acquire network. For avoid network, we get a reward which is measured by how close it is to the obstacles. So the closer to the obstacle the UAV is, the less is the reward. Similarly, for acquired network, we calculate that how far it is from the target. So the further the UAV is from the target, the lesser are the rewards. Finally, but we also add as another component into the acquired network, which is known as R of step. The R of step is a reward which is to prevent the UAV from exploring too much and wandering into the environment. So these two components finally form the reward of the acquired network. And then we have the reward for the packet network, which is given by R of collision and R of free. So whenever the UAV chooses an action and then a collision happens, then it will be punished by the reward known as R of collision. Similarly, for the pack network, we also find the loss through this loss function, and this is nothing but the mean squared loss, and this loss is known as the clip DRL loss function. Based on the loss in the pack network, then we choose an action for the pack network. This action is the action which is chosen is the action with the highest Q value in the pack network. So here the action which is chosen is a one-hot vector representation, which represents that among the total number of actions which are there in the pack network, which action is chosen. The final action is based on the action which in the packed network, combining with either one of the actions from the avoid network or the acquired network. In the experiment, the authors have designed a canvas of 500 by 500 pixel size, where each pixel represents 1 meter, and also each obstacle is also of radius of 1 pixel. The UAV has the sensor data from 18 different dimensions, and there are 2 layers of LSTMs, and the number of LSTMs in each layers is 120. We also tune the hyperparameters, since we are learning using a learning algorithm. Different hyperparameters which are learned here are the learning rates for the 3 networks, the avoid, acquire, and the pack network. Then we also learn the constants, the discount factor, and also the history length. Finally, for an optimizer algorithm, we are using the Adam optimizer. So in order to measure how is the quality of the navigation algorithm, we are measuring it on the basis of certain factors. First is the collision number. The collision number measures the total number of collisions the UAV performs. So the smaller the collision number, the better it is. The path length is the length from the source to the target. So the algorithm's goal would be to have the smaller path length. Then we have the success ratio. So for example, imagine that the experiments are done n number of times, and among those n number of times, the UAV actually reaches the destination without a collision for n0 number of times. So the success rate gives the ratio of both of them. Finally, we have the mutation number, which shows the deflection of the angle of the UAV in between 2 time steps. So the larger the mutation number, so the more likely that the UAV will crash. So our goal will be to keep the mutation number less as possible. We also test our model with other state-of-the-art DRL based method like DQN, one of the first reinforcement learning method, prioritized DQN, DDQN, and DRQN. The first experiment is the experiment for convergence. So we can see in this graph that for the layered RQN in this red curve, it converges at around 4,500 observations, and it also accumulates the most number of rewards. And in our convergence experiment, we will be evaluating based on 2 factors. One is how much reward it is accumulating, and what is the speed in which it is converging. So here we see the layered RQN performs the best with the highest number of rewards, followed by DRQN, which converges at around 4,000 ish episodes, and then followed by the other methods which take somewhere between 4,500 to 5,000 episodes. And also, if we see in this table, we can see that the layered RQN, it takes more number of episodes compared to DRQN. So this is due to its online learning structure, but we can see the duration of the computational time that we spoke earlier. It is much more faster. It converges much more faster. Next is the experiment for effectiveness. So here we see a scenario where we again have all the differently moving obstacles of different speed given by red, orange and yellow, the red being the most dynamic obstacle, and we also test the UAV with all of these approaches. Here you can see the paths taken by each of the approach. Now if you see for the DDQN, DQN and DPQN, all the three approaches, the path which are given in the bottom, these are the paths which are the highly dynamic, you can say, or which are the sudden trajectory changes. So but we can, if we compare that with this red line, which is for the layered RQN approach, we see that the UAV is taking much smoother path. So the other approaches, they are changing very suddenly in their trajectory. Also in the figure in the right, we can see the collision number for the layered RQN as given by the red curve is the least. It's around 4 number of collisions for 150 episode, which is substantially lower compared to the other methods. So in the table, we have summarized all the metrics in for all the methods that we use. So layered RQN, as we see, the collision number here is the least among them, and also the average path is least compared to the others, but the least average path is for DRQN. Success rate is also the less. It is 88%, and 16 is the mutation number. So we can see that the layered RQN, it has accumulated the highest number of rewards. Here we can see, and also it converges very good in a dynamic environment. It also solves the spare rewards problem, where each of the subnetworks, they are given rewards by allowing them to explore more. But the layered RQN is not very sample efficient, as we see here, because it takes more number of so here we see that it requires more number of episodes. But if you consider how its total rewards it accumulates and total time it takes to converge, I think it is much more better approach compared to the others. And also you can see the improvement in the success rate and the lowest number of collision number. All of these are due to the use of LSTM. So here in the LSTM, which is used to process the spatial and temporal data and all the correlations which are extracted from the LSTM, it helps the UAV to gather more scenario about the environment. Finally, the layered RQN can be generalized much better in the dynamic environment due to its loss function. The loss function, it updates its fusion rules based on the interaction with the environment. So as the environment changes, the rules also updates. So layered RQN performs again better than the baseline methods. But the layered RQN method also has certain pitfalls with certain shortcomings. One of the biggest is the reality gap problem. So when we are using the sensors in the real world, the UAV sensors will face a lot of noise and error. So this can lead to a faulty experiments. However, we have tested this method in a simulated environment where it is very easy to train number of episodes, and there are also less noise. But if we want to train the UAV with this algorithm in the real world, it would involve a lot of time, much more noise for the sensors, and also much more cost. So it is necessary to pre-train this model in certain simulation environment which are much more real to the real world, which are much more similar to the real world. So one of them is the air sim simulation environment. So it should be tested in one of those environments much more. Finally, to the conclusion, we see that the DRL method is much more advanced and compared to the other methods in a highly dynamic environment. This is because it is broken down into simple sub-problems and then they are merged together and solved. And this also allows the UAV to fly from the origin to target with in an obstacle prone environment with minimum number of collision and also doing the most exploration. But it would be better if we can, as I said before, if we test it in some simulation which are much more related to the real life scenario. So one of the future work can be testing it in one of the future into the real world scenarios, and also another important future work which I believe is to test the UAVs along with multiple UAVs. So all of them will work together to coordinate together to share their sensory data and then to find the path. So this can be a substantial improvement on this method going forward. So finally, I thank you for your patience and for listening this presentation, and I hope you like this topic. And until then, thank you. Goodbye.